Okay. Good evening, everyone. Welcome back to live session, NPTEL live session for the course Advanced Transition Metal Organometallic Chemistry. So today we will be taking up the lectures from the week 11, and at last we will be discussing about the assignment questions. So today we will firstly talk about the in-situ selective sharpless epoxidation. Last time what we ended up having certain kind of catalysis reactions which involves the Wacker process and also the epoxidation using some different methodology. Here we are particularly talking about the in-situ selective sharpless epoxidation. So the in-situ selective sharpless epoxidation, it's basically a titanium-based catalysis or epoxidation, we can call it as. That means it is involving a titanium catalyst, epoxidation of the allylic alcohols. So this is particular for this allylic alcohols. So as you can see, we have taken up a allylic alcohol where R1, R2, R3 can be anything. These can be any alkyl, alkene, or something like that. Can be anything for that matter. So we have an allylic alcohol over there. And now the conditions for this epoxidation is different, and how we introduce the enantiomer selectivity, we need to have some enantiomer selective or chiral center into that. So here we are treating it with a peroxide or sugar oxide, and in presence of the DCM, maintaining the temperatures at minus 20 degrees Celsius, and the catalyst is nothing but our titanium isoperoxide. And if we are using a diethyl tartrate, which is having this minus and plus sign, which is having these are two enantiomers, plus and minus. And if we're using or treating it with this particular enantiomer, we will be ending up having chirality like this with a dash bond on the oxygen. That means the oxide is forming with particular enantiomeric form. And if we are treating it with a plus DET, it will be having this kind of oxidation. So how the enantiomer selectivity is being introduced, it depends upon what kind of chiral system we are using. So if we are using minus DET, that means the sign shows you like stereo selectivity of like in which conformation or this state they are present. And depending upon that, we are ending up having a particular enantiomer. The main point over here, the yield is really very high, which constitutes a range of 70 to 90%, and also the enantiomeric axis. That means we are particularly getting one product at one particular time. So this is the enantiomer selective sharpless epoxidation, which involves a titanium catalyst. So also we can have an enantiomer selective oxidation if we are having an alkyl or a aryl substituting alkenes, for example, this one. But here we would be having a different catalyst and the conditions would be different, because in that case we were having allylic alcohol and this was the oxygen transferring agent, whereas here we are not adding any peroxide. So in absence of peroxide, so therefore now we can take this particular system as this arene ring as a phenyl or star and IO. So this becomes a oxygen transfer or oxidant, we can call it as. So this is your oxidant, which will give an oxygen to your metal system, and then that metal catalyst, which is having an oxygen, it will transfer to the alkene in forming an epoxide with the enantiomer selectivity, because here we already have a chiral selene or the ligand system with the catalyst system. And ultimately, this particular oxidant will get reduced and it will give you the PHI over here. So how this mechanism is occurring? So a chiral selene manganese 3 complex is actually acting as the catalyst in the enantiomer selective epoxidation, which is converted to the selene manganese 5 oxo. So here we have the species. This is our catalyst. The star is representing your chiral ligand, and here the ligand is selene. And when we are using an oxidant, what we have chosen over here, I am putting a star mark, which is PHI star. I am referring as this 2,4,6 trimethyl benzene, PHIO. Because of this oxygen, this will give or make a manganese to manganese oxo. This is a manganese oxo. And ultimately, this oxygen is transferred to this alkene bond. So this step is now called as transfer of oxygen, and therefore the epoxide formation occurs. And the chirality, as you can see, that's maintained. So the highlighting point of this particular enantiomer selective epoxidation using the manganese catalyst, which is itself having a ligand system or the chiral system. That ligand is itself a chiral, which is introducing the enantiomer selectivity. The transfer of the oxygen atom to the alkene occurs without the participation of transition metal and the carbon intermediate. So they are actually not in coordination, or they are not making a direct bond. It's just a transfer reaction. That's why this is a highlighting feature of this particular enantiomer selective epoxidation. So here in the epoxidation thing, what we have, we will just say like this. Second. So first we saw the sharpless epoxidation, which is mainly focusing on the allylic alcohol to give you the epoxides. And if we talk about the chirality, it will introduce the chirality. It happens in presence of a peroxide, and the highlighting feature is the titanium. So this is our catalyst over here. Right. The second thing that we see right now was again an enantiomer selective epoxidation to the substituted alkenes or arenes in presence of an oxidant, which is nothing but your pH star IO. You have seen what is pH star I am mentioning, and in the presence of a catalyst, manganese based catalyst, which is containing a chiral ligand, and it will also give you the epoxide with a enantiomer selectivity. So this was about the epoxidation. Now we are moving from the epoxidation, that the formation of epoxides, to another type of catalytic reaction, which is very, very important. As the name suggests, it's a water gas shift and Fischer-Tropsch reaction. These are two different reactions, but they are called as a complementary to each other. So both the reactions are counteractive. One is oxidation, one is reduction. So water gas shift reaction is the oxidation of carbon monoxide, whereas the Fischer-Tropsch reaction is the reduction of carbon monoxide. So though the Wacker process opened up the doorway for the organic metallic chemistry, later the field was mostly based on the carbon monoxide, that's the C1 chemistry. So in Wacker process, we have seen that how the ethylene is getting oxidized to your acetaldehyde, right? So that was one oxidation, but here we are talking about like mainly now the field is going towards the C1 chemistry, and these two reactions are very highlighting where we see the oxidation of your carbon monoxide and reduction of carbon monoxide, giving different products. So firstly, the synthesis gas is comprises of the carbon monoxide plus H2. So the industrial processes mostly uses methane, ethylene, propylene as starting materials. You have seen in many reactions where CH4, your ethene, CH2 double bond CH2, or your propylene, they are being used as a starting materials to get two different kind of synthetic compounds which are obtained from the natural gases. So what is the origin of these particular starting materials? That is nothing but the natural gases and from the crude oils when we get that. So once the observed sources started depleting, as we already know that natural sources are depleting and we are looking for some other alternatives. So the C1 building block becomes very important. So their carbon monoxide or CO2 becomes very, very important source to get these kind of starting materials to get different kind of products. That's why the importance comes into picture. Now, the synthesis gas, carbon monoxide, can be obtained from the controlled combustion of the crude oil. For example, reforming of the natural gases. If I'm taking methane and if I am treating it with water or steam, so it will give you carbon monoxide with the release of H2, and this is the enthalpy or the energy, that amount is being, since this is 2 plus 205, so that is endothermic, and if we are releasing the energy, that would be the releasing and accepting of the energies with the endothermic and exothermic processes. And if we are treating it with the oxygen, the combustion does involve the oxygen. If you are treating it with that, it will give you again carbon monoxide with 2 moles of H2 with this much amount of energy. The second way to get the carbon monoxide, this we are talking about the sources of carbon monoxide, because Why do we need to have the carbon monoxide as a source, as a starting material? Because from this we can get methane, ethylene, propylene, and many other methanol and other value-added products, which could be a source for many synthetic products which we come or daily use, we use daily, or if they are having medical application and all those things. And here we are talking about the sources from where we can get the carbon monoxide. First is the reforming of the natural gases. Second is the coal gasification. For example, we have taken coal is nothing but the carbon. When it is being treated with the H2, then it converts to carbon monoxide and H2 with this much amount of energy. So this was the lecture 51 was about certain description about the epoxidation. We have termed it in two ways, like sharpless epoxidation, and how we can have the epoxidation on epoxide formation on the alkene bond, which are having a substituent of alkenes or arenes in absence of any peroxide, but with the different oxidant. There we are using a manganese complex catalyst, and in sharpless epoxidation we treated with the titanium catalyst. Then we shifted our concern from this epoxidation to the carbon monoxide production or reduction or the oxidation, the water gas shift reaction and the Fischer-Tropsch reaction. The description about these two processes we will be taking up in next lecture. So here, firstly, we are talking about the 52 lecture is about the water gas shift reaction, which is nothing but the oxidation of your carbon monoxide. So here, as you can see, the water gas shift reaction, the oxidation is happening using the water. And the catalyst that we are using over here, generally it is being used with the iron or copper catalyst, and the catalysis is in heterogeneous mode. So everything would be happening on the surface. And the temperature, as you can see, they are greater than 200 degrees, and ultimately they will be releasing carbon dioxide with H2. So the significance of the equilibrium. So as you can see, this reaction is under equilibrium. So the forward and the backward are both the rates are constant or the similar. The significance of the equilibrium lies in the exploitation of the reducing power of carbon monoxide to produce H2 from water under mild condition. So the removal of carbon monoxide from the gas mixture for the Haber-Bosch process, which is involved for the synthesis of ammonia, H2 enrichment of the synthesis gas for Fischer-Tropsch reactions. So if what we saw that water gas shift reaction was occurring in heterogeneous medium, but now here we are talking about the homogeneous thing. As the current heterogeneous catalysis involve high reaction temperatures, as we saw that it was T greater than 200 degrees, which can affect the equilibrium. Equilibrium is never been favorable when the temperatures are very high, and also it can affect the stability and the longevity of your catalyst. So that is what has been written over here, which is unfavorable for the position of equilibrium for the wet water gas shift reaction. Therefore, now more development is happening in the homogeneous catalysis. So the main target is the nucleophilic activation of carbon monoxide, which is done by the coordination of carbon monoxide to a transition metal, followed by the addition of the nucleophile. So here, the mechanism with the homogeneous catalyst has been defined. If we have a transition metal, this is nothing but your transition metal complex. And here we are having carbon monoxide. So coordination has to be, first the coordination will happen. Once the coordination will happen, because this carbon is being electrophilic in nature, so nucleophile gets activated and therefore it attacks on your carbon thing. Now the main important step for the carbon monoxide plus water to give you the CO2 plus H2. So what catalyst we are using and what is the name of that reaction? It's a Haber-based reaction where we are using an iron carbonyl hydride complex. Firstly, the carbon monoxide gets involved with the loss of H negative. This is coming and H negative is going out. Since the H negative and we are giving water as a source, H negative and H2 is nothing but H positive plus OH negative. So these two, negative and positive, will combine together to release the H2, release of hydrogen, and ultimately the OH negative with hydroxide anion, it will come into picture. Since this is a neutral complex and also having carbon monoxide, which is totally electrophilic or pi acid in nature, OH can readily attack on the carbonyl carbon, making this acid, and ultimately it will release the CO2 will release, and it will give the hydride complex back. So this is the Haber-Bosch reaction where we are converting the carbon monoxide into carbon dioxide. This is called nothing but the water gas shift reaction. So another possibility, if at the start of it, there could be two possibilities. Firstly, the carbon monoxide is attacking. It is coming, first attack is of carbon monoxide. Or the second possibility that H2 is involved at the first step. So earlier what we saw that carbon monoxide insertion was, or the coordination was the first step. But here the water is releasing your hydroxide. Because this H negative is there, it will definitely take up this H positive from your H2O, and one more H positive will come because this is having a negative charge which will take up the positive into picture. Two hydrogen will be there with the iron and it will release out the hydroxide. Now, since two hydrogen are there, they can easily form the hydride and they can easily release as the H2, which will completely give you an iron carbonyl. And since we are having the carbon monoxide now at this step, we are involving the carbon monoxide at the third step. The carbon monoxide will give you again the carbonyl, and since we released the hydroxide at the first step, the hydroxide will come and give you the acid. It will release the carbon dioxide, and ultimately you will end up. So the both ways, either the carbon monoxide is coming at the first step or the water involvement is happening at the first step, we will ultimately ended up having the carbon dioxide with the release of H2. And this is the two-way possibilities of the Haber-Bosch reaction, which is nothing but your water gas shift reaction. Now the catalytic water gas shift. So the metal carbonyls in general catalyze the water gas shift reaction in basic media, as you have already seen. So the species, this rhodium I2CO2 negative or the rhodium 3I5CO whole 2 negative are also able to catalyze the water gas shift reaction, which is present in this particular system. So what is the mechanism if we are using the carbonyl system? So initially we started with the rhodium 3. Carbon monoxide has to get oxidized, right? So some system should be there to, if this is getting oxidized, some should be get reduced. So what is happening? That rhodium is taking up the electrons and it will reduce to rhodium 1. Carbon monoxide goes to carbon dioxide with the release of 2H positive. Ultimately, this rhodium 1 will again react with the 2H positive and it will release the H2 and get oxidized to rhodium 3, and the catalytic cycle continues. So ultimately, reaction is the nothing but your water gas shift reaction, but the catalyst has been involved from rhodium 1 to that +1 to +3 oxidation state system. So this lecture was about So what we have seen that water gas shift reaction is your oxidation of carbon monoxide to carbon dioxide, whereas Haber-Bosch reaction we saw using the HFeCO whole 4 negative. And ultimately, we also saw that how we can have the catalytic water gas shift reaction using rhodium 1,3 catalyst system. And the next lecture is now about the Fischer-Tropsch synthesis, which is nothing but your reduction of carbon monoxide. So water gas shift, as we have seen that it is both homogeneous and heterogeneous, but now we are favoring the homogeneous thing because to carry out the reaction at low temperatures. So the water gas shift reaction is carried out in heterogeneous catalysis till date. since we need to have a large scale production and on an industrial level for immense production, we cannot just rely on the homogeneous system because the productivity or the maintenance would be difficult. So heterogeneous will be giving you a large amount of the product. But the advantages of homogeneous catalysis is the lower energy requirements, which is actually favorable for the equilibrium positions at the low temperatures and high tolerance towards the catalyst poisoning that we have just discussed. Like the heterogeneous things are mainly having two side effects. Firstly is like requirement of the high temperatures to activate the surface. And second of all, like many active sites are there. So that would lead to a lot of products. So selectivity reduces. So higher temperatures and lack of selectivity. So these are main drawbacks for the heterogeneous, and that's why homogeneous catalysis is now being taken up into consideration and more complexes are coming into picture. So in nature also, homogeneous pathway is followed in carboxytothermos and hydrogenoformans bacterium, where the oxidation of carbon monoxide to carbon dioxide happens. So naturally also homogeneous path has been seen where the coordination with the carbon monoxide and the hydride is coming into picture. Now we are moving to the Fischer-Tropsch synthesis. This is your carbon monoxide to hydrocarbons processed, the reduction of your carbon monoxide, which is not limited to alkanes or alkenes, but also it can synthesize the methanol, glycols, aldehydes, and whatnot. So if we are treating the N moles of carbon monoxide with 2N of H2 using the particular catalyst, it will ended up having a hydrocarbon or whatever you want to have. So this is the energy thing. The Fischer-Tropsch synthesis generally operate under the heterogeneous catalysis where the low specificity is the problem, because as I told that because of the more active sites on the surface, it cannot control or it cannot be specific towards a particular product. So that's why it ended up having a lot of products. So that is the main thing. So synthesis gas, if we are using the carbon monoxide with the H2, it in the presence of these catalysts like cobalt, thorium oxide, magnesium oxide, or silica gel or something like that. Firstly, look at the temperatures which are very high temperatures. And as you can see, it is giving 50% petrol, 25% diesel oil, 25% waxes, so low selectivity. So that is a major problem. Therefore, the heterogeneous catalysis was developed by AG from 1936, which was abandoned from after World War II. South Africa still uses cheap polar source of synthesis gas to fulfill all the fuel requirements. That means using the H2 and carbon monoxide. This is iron oxide catalyst, and look at the temperatures very high, and they could go up to petrol to 70%. That yield has been increased. Now, if we talk about the homogeneous thing, so what could be the best possible catalyst that has come into picture? The homogeneous catalysis is unlikely for the production of synthetic fuels owing to the size of the plant required. The main point that I told, like for the industrial application, we cannot just rely on the homogeneous because the productivity is somewhat less, and heterogeneous, they do provide a large amount of the product. But for from the perspective of other Fischer-Tropsch products, that means homogeneous catalysis may be an important area where the C1 chemistry is looked into the picture. And if you are treating the carbon monoxide with 3 moles of this H2 using the rhodium catalyst, and just temperatures and bars, so we ended up having the ethylene glycol as the product. So the soluble rhodium carbonyl clusters catalyzes the formation of the ethylene glycol. So now methanol is formed instead of glycols at the low temperature pressures. As the catalysis involves harsh conditions, it's not in practice since you have seen that it involves 3000 bars and 250 degrees Celsius, which is very, very high and harsh reaction conditions. Therefore, however, there's a huge demand for glycol because it's an antifreeze building block for many polyesters. Currently, it is produced from ethylene to ethylene oxide and hydrolyzed subsequently. So right now, still the work is going on to maintain the low temperatures or the mild conditions to get the glycol. but till now, not much has been seen in this particular thing. Now we will look into the mechanism of Fischer-Tropsch reaction, how it is happening. So here M is the active site, it could be heterogeneous or the vacant coordination of the homogeneous. So M could be anything. So how the mechanism is actually occurring? Firstly, the metal, which is a transition metal, the carbon monoxide coordination happens. So the first step becomes the coordination, and then the nucleophile will attack, which is the hydride. It will make this formal complex. Or it could, when we treat it with another molecule of H2, it could give you this formaldehyde, which is nothing but HCO1OH. It could coordinate as a eta to form, and then after hydrogenation using the hydrogen gas, it will give you the methoxide, and again with this particular thing it will release the CH3OH and MH bond. So therefore we will be ending up having the methanol over here. So how we can have the formaldehyde or methanol? And the other way, if we have a formal complex and if we treat with the H2, where it is only bound with the carbon, that means the eta1. If both oxygen and carbon are involved, that is called the eta2. So here, when it gets reduced, it is already having one H with the loss of water. It will reduce to CH3, and on insertion of carbon monoxide into it, it will give you CH3CO. So if we take up this MCH3 with the treatment of hydrogen, it will release the CH4. And if we have this COCH3 treatment of H2, it will give you the ethane molecule, and again treatment, it will give you COCH2CH2. So this is way number of possibilities are there with the amount of hydrogen that you are giving, and what kind of coordination it is having. So it depends upon the number of moles of the hydrogen. Also, it depends upon the metal that you are choosing, whether it will go for the eta1 or it will go for the eta2. So either it is having more electron density, what kind of ligands are in the environment. So how it is supporting. So number of products could be possible, and we can specify it in case of the homogeneous thing, because in heterogeneous there could be many active sites, so we cannot control the specificity of it. Now moving towards the lecture 54, which is again which again involves the Fischer-Tropsch mechanism. So here Fischer-Tropsch reaction, the mechanism for the polymerization of the methionine groups at the catalyst surface. So this is nothing but your heterogeneous systems. We are talking about how the polymerization occurs. So firstly, this carbon monoxide is getting reduced. That means in the surface, this is a surface where this is your surface, metal surface. And as you can see, they are getting carbon monoxide and H2 are getting activated. Firstly, the bond breaking will happen and new bonds making will be happening. And ultimately, the oxygen and the carbon, H and H, all will be disintegrated. Now it will lead on to the hydrogenation. It will lead to form the CH3, CH2, and CH2. Then they will combine together to form this CH3, CH2, and CH2CH. Again, in presence of H2, it will all will get combined, and this will give you a chain of 4. After the beta hydride elimination, this is alpha and this is beta, and this hydrogen will go off, and this will give you a polymer. Where we started up with this carbon monoxide, we ended up having the chain of 4, and ultimately this process will continue because we have the carbon monoxide and H2. So this is way how the polymerization occurs. And the last lecture is about the carbonylation of the alcohols. So carbonylation of the alcohols, that means the methanol to acetic acid. So we are having CH3OH, and it is going to CH3COH on involvement of carbon dioxide, carbon monoxide. Also, this is called as Monsanto acetic acid process. So we are using synthetic gas, which is carbon monoxide and H2. In presence of the copper catalyst, we first will get the methanol. So this is the first thing that we will be getting. And then it will involve another catalyst. This is second catalyst is involving in presence of carbon monoxide. This involves the high iodide source also. Why it involves, we will see in the next slide. So under temperatures of 180 degrees and 30 bars, it will lead to the acetic acid formation with the selectivity of 90%. The capacity is per annum 10 to the power 6 tons has been can be generated. So this is how we can convert the methanol to acetic acid. So here it is very important mechanism. So the first step is, firstly, we have seen that rhodium catalyst was involved. And secondly, the iodide source was there. We will see why they are important. So as you can see, because this is the second step of that main Monsanto reaction. First step is just simply the conversion of carbon monoxide with H2 and giving methanol. So this is the product from the first step, first reaction, product from first reaction. This methanol, when it is being treated with HI, this is your iodide source. So once it is treated, it will form your methyl iodide, which is very, very important to participate in the reaction and will produce water, which is also important. So the first step is the oxidative addition. Of your methyl iodide. So here, as you can see, methyl and iodide are now trans to each other, and they have been added onto the rhodium. It was earlier in +1, now it would be in +3 oxidation state, as we saw that it could undergo from 1 to 3. Now, what will happen, because we have a carbon monoxide, it will easily undergo the insertion. Insertion of carbon monoxide is a second step, so it will form COCH3. Again, we have carbon monoxide in bulk, so carbon monoxide will come into picture and it will get coordinated with the rhodium. And since the COCH3 and iodide are cis to each other, they will leave out. This is called your reductive elimination step. And it will give you again this RHII and carbon monoxide, which will give you again the same thing back. Now here, if you see properly, we want acetic acid as a product, and it is giving a C-role bond OI. And since we remember that at the first step itself, we generated the water. On treatment with water, it will release the HI and it will take up the OH negative, which will coordinate with your carbonyl, and it will give you the acetic acid as the product. So this is very important mechanism for the synthesis of acetic acid from the methanol in presence of the carbon monoxide. And now the role of iodide ion is to convert the methanol into the higher electrophile methyl iodide. So we started with the HI, and it was being used to convert this to a higher electrophilic center, which is CH3I, because of the more electronegative thing. Now this method can be applied to next higher carboxylic acid synthesis as well. And industrially, acetic acid is used in the acetic anhydride synthesis. So this, firstly, we produce the methanol from the synthetic gas. Then from there, we produce the acetic acid. Now this could be used in producing the acetic anhydride. So now the carbonylation of the alcohols, the production of acetic anhydride under the homogeneous condition, so which involves the Tennessee-Eastman or Halcombe SD process for the carbonylation of methyl acetate. So the first step, you already know that in presence of the copper catalyst, we are producing the methanol, and this acetic acid, when it comes from the Monsanto acetic process, it will give you the methyl acetate. So this is nothing but your methyl acetate, and the carbonylation is now being happening, and this is giving you anhydride. So this was, so here in this particular lecture, what we saw that carbonylation of your alcohol, that means carbon monoxide with H2 is giving methanol in presence of copper catalyst, and if we are using a rhodium catalyst in presence of iodide source and carbon monoxide, it will lead to form this CH3COO. This is nothing but your Monsanto acetic acid process. And second, if we are treating this carbon monoxide to H2, to ethanol, and treating with the CH3COH acetic acid, it will first give you this CO2CH3 methyl acetate, which will get carbonylation, and it will lead to form your acetic anhydride. And this is named as Tennessee Eastman method. So this is it, what we have seen in this particular week, that we talked about certain epoxidations, sharpless epoxidation, and also some enantioselective selective epoxidations on the substituted arenes or alkenes in presence of manganese catalyst and the titanium catalyst. Secondly, we saw the importance of carbon monoxide reduction as well as the oxidation, which involves water gas shift reaction, which is your oxidation of carbon monoxide, and the Fischer-Tropsch reaction, which is the oxidation of carbon monoxide. To give you value-added products, generally heterogeneous catalysts have been used till date because of the industrial production, but one cannot ignore the high temperatures or the selectivity issues that come from the heterogeneous thing. So many homogeneous catalysts are also coming into picture, but the scalability is an issue still. So people are working on it. And then we saw how we can get the methanol from the carbon monoxide, and then it can be converted to the acetic acid, which is called the Monsanto acetic acid process, and the mechanism has been well explained. And then from the acetic acid and a combination of methanol in presence of carbon monoxide, how we can ended up having the acetic anhydride. Also, we saw the polymerization of your methylene from the synthetic gas, like carbon monoxide and H2 on the metal surface, how it is giving you a poly product. So this is it for the week 11. Now we will quickly take up the questions from week 11 assignment. Hope you have understood the concepts well. If not, then do drop a message or a mail so that we can take up your questions, and I'll be sharing these slides with the full explanation to you guys. Now we will take up the questions. So I hope you can see the questions. So the first question, since see the questions are more or less coming from your slides itself. So if you have read or listened to the lectures very carefully, because we have just repeated the concepts that has been already been discussed by the professor. So they would be like straightforward questions, but I can help you to explain it more. So the product or the products of the following reaction is or are. So here, as you can see, first you have to see like what is happening. This is nothing but your substituted alkene. And this is your oxidant. Now, as you can see, this is your catalyst with chiral ligand. Now it is nothing but the epoxidation that we know already. Manganese has a tendency to get to form manganese oxide, and then it will transfer it to epoxide. Now, since we are using a selene, which is having that star, that means chirality is there, so it will give you an enantiomer. So what kind of an enantiomer is going to form? So this is not going to change. R1 and R3 are not going to change the positions and the initial selectivity. So it will ultimately, the mechanism will go like this. If it is having star is nothing but the chirality. So in presence of this oxidant, it will form MNO, and then in presence of this R1, R3, R2, it will transfer and it will form R1, R3, and R2. So this is the right option, and your option B is your right option. This is also nothing but your enantiomer selector. enantioselective oxidation, which we have discussed in the lecture, might be 51 or 52. So you can go and see the explanation for better understanding. Now, the second question is the carbon monoxide is converted to carbon dioxide by. So if you remember clearly, carbon monoxide when treated with H2, it will be having an equilibrium with carbon dioxide plus water with certain amount of delta H. So this is nothing but your reduction step. Sorry. So this is your oxidation from carbon monoxide to carbon dioxide and in presence of the water. And for the oxidation, we know that water gas shift reaction is our answer because the Wacker process is nothing but the conversion of your ethylene to acetaldehyde. So this is the oxidation from ethylene to acetaldehyde. Fischer-Tropsch reaction is the reduction of carbon monoxide, and water gas shift reaction is your the conversion or oxidation of carbon monoxide to the carbon dioxide. So option C is the right one. The reduction of carbon monoxide by hydrogen to hydrocarbon is performed by. So here we have now, earlier this was thing, it will give you the hydrocarbons. So this is nothing but the reduction of carbon monoxide, and Fischer-Tropsch is that reaction where the reduction happens. The final product is the Tennessee-Eastman or Halkan-Estey process. So we saw two processes. One was the Monsanto acetic acid. The name suggests that it is giving you the acetic acid formation, whereas the Tennessee one is involving the formation of acetic anhydride we just saw in the last lecture, where it goes from carbon monoxide to form methanol, which is being treated with acetic acid and give you the methyl acetate, and ultimately leading in presence of carbon monoxide, it gives you acetic anhydride. So the final product is nothing but your acetic anhydride. That's the C option. Water gas shift reaction is catalyzed by, as you have seen, that iron and copper we have seen for the water gas shift, that carbon monoxide plus water thing that involves this also and some other things. So iron or copper. So that is the first option. The composition of synthesis gas, that is also very straightforward, that synthesis gas in nothing but your combination of carbon monoxide with H2. These are very straightforward questions. So the following transformation is achieved in selectively using. So here this is a bit important. Firstly, you just need to identify this is nothing but your allylic alcohol. And this is your peroxide, which is the oxidant. And catalyst is nothing but your titanium isopropoxide. So here this reaction is your enantioselective. Sharpless epoxidation, where the alkene is converted to the epoxide. Now, if you see properly that for as you can see, the catalyst also is not having any chirality, no chirality in catalyst, nor oxidant, and nothing like that. So how the chirality will be introduced? It needs to have some system which is having the chirality. So if you see the B and D option, they are not chiral. Only the A and C are chiral. Now we have already seen, if we start with the diethyl tartrate, we will end up having R2, R1 with this kind of enantiomer. And if we are starting with the negative, we will be ended up having so for because it is having a wedge one, C option is the right one. So you need to be firstly very careful to identify chiral ligand or the substrate is very important. The region is very important. If the chirality is not in your system, and out of the two, which one would be preferred? You have to see, because in the negative, it is not like you have to. As you can see here, the wedge is over there, so it will give you this kind of oxide. If we'll start with this positive, which is having dash thing, it will give you a dash over here. So this is the way you can just remember it. The following reaction is an example of. So as you can see here, here the zirconium complex has been given, and already the carbon dioxide coordination has happened. Now in the second step, as you can see, this is an insertion is happening. The carbon monoxide is going into the metal and hydride bond. So this is not an oxidative reaction. This is neither a reductive elimination. It's just a migratory insertion of your carbon monoxide to the metal hydride. And transmetallation is not at all happening because there is no metal over there which is transferring any of its substituent. The ninth question is very interesting that we have just seen in the lecture slide. The compound 1 and 2 of the following reaction sequence respectively are. So here, this is a synthetic gas, as we have seen and read a lot of times. So synthetic gas, the copper catalyst, it will give you 1. So what is 1? 1 is nothing but your, we need to identify. And if we are giving a condition of carbon monoxide, that means carbonylation, in presence of the rhodium catalyst and an iodide source, it will give you what? So this second step is nothing but the Monsanto acetic acid formation. That means the second has to be CH3COOH. And we know that it is coming from only the methanol. So the first has to be methanol and the second will be acetic acid. So this is your D option is the right one. So even if you know the second one, you can identify your first one very easily. And the last question for this particular assignment is the catalyst used in the Tennessee Eastman or Halgan-Essig process. We have seen that it is required to make that acetic acid and then convert it further to acetic anhydride. So rhodium catalyst having that iodide is very, very important. So this is the catalyst which is being used for Tennessee Eastman method, which is nothing but the acetic acid, acetic anhydride formation. So this is it, what we have seen in the question, and these are the possible answers to it. And if you have any doubt or any clarification you want on the answers or the mechanisms, then you can just drop a message. We can just discuss it very quickly. We'll keep this as it is.